Okay, so we want to look at what an actual limit is and what it represents if we're letting x approach c. So let's say we have some function f. So right now it looks like the height of f at c is L. We can put lines here. It looks pretty accurate so far. But we want to show that if we're getting closer to c, then we're actually getting closer to L. That means its limit. So let's say we have a very small number, delta. Then we're going to add delta to c, but we're also going to subtract it from c. Now we're going to do the same thing to L. We're going to add a really small number that we call epsilon to it, and we're going to subtract it. So what we have here is this little box that we can form around C and L, or the point CL, we should say. So our claim is that that delta and that epsilon that we added to C and L respectively have some relationship. It might be delta equals epsilon over 2. It might be delta equals 6 epsilon. We don't know what it is, but there is some relationship there. And so what that means is if we make delta smaller, epsilon is going to have to become smaller as well. So let's let delta become smaller. Now look what's going to happen here. C minus delta, C plus delta, they're going to get closer together. They're going to get closer to C. And look what happens to the box when that happens. Epsilon also got smaller. The box is closing in on that orange point there. If we do it again, notice that orange dot is still inside of the box. And if we were to zoom in on the function and just keep doing this repeatedly and repeatedly, the dot's always going to be inside of the box. It's never going to come outside. And what that means is we found the limit L. As x is approaching c, f is approaching L. And as long as it doesn't come outside of that box, we're good. We found it. So if we can make the walls close in on c, that means the ceiling and the floor are going to close in on L. And that means that we have the limit.